Hey everyone, and welcome back to our third video in the series, confusingly called Part 2, where we will be writing the selection operator for our very own genetic algorithm. In the first video of the series, check it out here, we covered the high-level concepts of the crossover portion of the GA. In that video, I said that we picked two parents from the population, and I promised that I would explain the method used to do so in a later video. I like to keep my word, don't ask me where the car racing video is, so here we are. There are many different selection operators that could be used that will yield good results. In this video we are going to cover two of them. The first will be a very basic tournament selection, and the second will be the biased roulette wheel approach that I mentioned in the original video. Before we start, there is an updated GitHub repo linked down below. Even if you followed along with the first video, I have added a few things there that you might want. If you didn't follow along with the first video and want to do that before we start, you can click here. Otherwise, you can pull the current repo linked down below. So the first change that I made was to add some text to our screen that tells us the distance of the path that we're currently visualizing. Just a heads up, this distance is in pixels. This will help us as we get to the breeding stage because we'll be able to watch our result improve over time. The second thing I changed was that in our main game loop, the update method for our simulation screen now takes in the best neighbor and not just its sequence. I'm using this behind the scenes to grab the fitness to be able to display it on the screen. Now that that is out of the way, let's get started. Heading back over to the world class, let's start working on this do generation method. What we want is to generate the same number of offspring as we currently have individuals in the population. So let's create a new list to hold our offspring, and then let's create a loop that we can use to create our offspring. So now each loop, we want to get two parents, we then want to perform the crossover and then potentially perform a mutation. For now, we'll leave the crossover mutation portion, they will be completed in a future video, but let's create a new private method in the world class called getParent. And let's say that it returns a neighbor. Now getParent will look through our population and then return some individual based off of some logic. Then inside of our main do generation loop, we need to get two parents, a mother and a father. So we can do that by typing var mother is equal to getParent and var father is equal to getParent. Jumping back to the getParent method, we are going to have two selection modes with an equal chance of using either. We can do this using the random.nextDouble, which generates a number between 0 and 1. Then we can say that if the number generated is greater than 0.5, we'll use the tournament selection. Otherwise, we'll use the biased random selection. Then let's just create a method to do each of these. So we can type private neighbor tournament selection, and then this isn't going to take in any arguments, and we'll also create private neighbor biased random selection. So now in our getParent method, we can simply return the appropriate method. So if the value is greater than 0.5, we'll return tournament selection, else we'll return biased random selection. So how does tournament selection work? Tournament selection is one of the simplest selection techniques. It works by randomly choosing two individuals from the population. With this selection technique, each individual has an equal probability of being chosen. We then get the fitnesses of both individuals that were picked, and whichever has the higher fitness value is selected. So this in its way is biasing selection towards fitter individuals. As we pick our two individuals, we want to ensure that they're both unique and we haven't accidentally picked the same neighbor twice. So this actually introduces a small quirk in this selector. Imagine that we pick the least fit individual. Any other individual in the population that we select will have a higher fitness value. This means that the least fit individual could never be selected as a parent using the selector. Now, while this isn't ideal, it shouldn't impact us too much, so we're not going to worry about writing any logic to handle this case for now. Jumping back to the code, we'll grab our first candidate parent, candidate 1, by indexing into our neighbors, and to select a random index, we can type random.next and pass it in the population count, which will generate a number between 0 and population count minus 1. Then we'll do the same thing to grab our second candidate. Immediately after, we want to handle the case where the two individuals are identical. So we'll say that while these two individuals are the same, we'll randomly choose a new candidate 2. This may not be the best way to do this, but it's extremely clean and 99% of the time should immediately return false. Then, after this loop, we know that we have two unique individuals. We can test them for their fitness values and return the appropriate candidate. While our genetic algorithm is running, we want to ensure that we have a constant diversity in our population. However, you can imagine that if you have offspring that are identical to their parents, it's very possible that after a number of generations, each individual in the population could be identical. So I know what you're thinking, how does this happen? Unless we take the first individual out of the population after they're selected, there is a probability that you'll select the same individual as both the mother and father. Now, the probability could be quite low depending on your selection method, but there is one key thing I've learned working with GAs: don't ever leave something not happening up to chance. Due to the very large number of generations, even something with a minuscule chance of happening will always find a way and it will ruin your day. Okay, so rant over, moving on. Let's jump back to the do generation method. We want to do the same thing here as we did in our tournament selection. So we'll add a while loop to ensure that we can never select two offspring that are identical. So we can type while mother equals father, father equals get parent. So how does biased random selection work, and what the heck is a biased roulette wheel? While tournament selection biases towards fitter individuals, if one individual is much better than the others, it is not proportionally more likely to be selected. This could be a good or a bad thing depending on the situation, but it's just something to keep in mind. The biased random selection approach doesn't require this consideration. It works like this. Let's say you have a roulette wheel where each of the items on the wheel is one of our potential solutions. If we were to spin the wheel, we would be equally likely to pick any individual, just as we did in our tournament selection. But what if we could make each segment on the roulette wheel bigger or smaller depending on how good the solution is? That way, if we make the better individuals bigger and we make the worse individuals smaller, when we spin the wheel, we would be more likely to choose an individual that is better, while still keeping the potential for our less fit individuals to be selected. We can then take this wheel concept and convert it into something that we can code. For instance, a distribution over the values 0 to 1. Now it becomes quite simple to select a parent. We can generate a number between 0 and 1, and whichever individual our value falls in, that's the one that we'll select. Now, whichever individual our value falls in is actually easier said and visualized than it is done. So to do this in the code, we'll need to create an array of cumulative values like so. Then, when we generate a random number, we'll loop through this list until we find a value that is higher than the random value that we generated. If this doesn't intuitively feel like the same as randomly picking from the population based off their respective probabilities, I'd encourage you to give it a go with a few numbers, although hopefully the animations here have helped. Now before we jump back and implement this in the code, I want to talk through the processing that has to be done on our fitness values in order to treat them as we've described previously. We currently have our fitness values of each of our individuals stored as their raw distance value. Therefore, we need some method of converting individuals into a value that represents how likely they are to get picked. Where individuals with shorter distances are more likely to get picked, and individuals with longer distances are less likely. So the way that we're going to do this is by first calculating the sum of all of our fitness values. Then we are going to loop over each of our fitness values and replace them by the sum divided by the values themselves. This gives us the inverse proportion of the total paths that specific individual is taking up. In other words, the shorter the path, the higher the value. At this stage, the proportions for each of our individuals are effectively representing the probability of selecting that value, but they need to be normalized. To normalize, we calculate a new sum and then divide each of the values by that sum. So let's jump back to the code and do that now. The first thing that we need is the sum of all of the current fitness values. We can get the sum by typing var_sum is equal to Neighbours.Sum, and then we have to provide a delegate to tell C# what we want to sum. Next, we need to create our proportion list. So we can do that by typing var proportions is equal to Neighbours.Select, and then we want to select the sum divided by the fitnesses. Next, we want to normalize each of the proportions to be between 0 and 1. So again, we can take the sum Then we'll create a new list of normalized proportions by iterating over each of the proportions list and dividing them by the proportion sum. So now that we have each of our individuals with each of their probabilities being selected, we need to create our cumulative proportions. So let's create a new list called cumulative proportions, which is going to be a list of doubles. Next, we will define a cumulative total variable to track our total so far. Then, let's iterate through each of our normalized proportions and add the cumulative total. Okay, so we are getting very close now. So now that we have our accumulated values, we can generate a value between 0 and 1. Let's call it selected value. Then we can loop over each of the values in our cumulative proportions. And the first one that we find that has a value higher than or equal to the selected value, we will return that neighbor. Then at the very bottom, we want to throw a new exception if we ever hit this, which would mean that our normalized fitness values didn't sum up to 1 or something crazy like that. If this seems like an excessive amount of work to do for each individual, kudos to you for recognizing you are 100% correct, but just hold out for today's challenge question. Next, we need to go back to our run loop in our game class and remove the comment for do generation. The very last thing that we need to do if we want to see some visual feedback is to go back to our world class and temporarily update our getBestNeighbor method to instead return getParent. Awesome, so hitting run, we can see that once per second our paths are updating, which means that our parent selection is doing something, and it looks like we're in an excellent place to start working on the crossover. So let's quickly just go back and remove that getParent call from our getBestNeighbor method. Okay, so that is it for today. As with the last time, I'm going to leave you with a challenge question. What huge speed improvement could we get by modifying our biased random selection method? Small hint, perhaps there is some code in there that doesn't need to run every time this method is called. Best of luck, and please leave your comments with suggestions down below. I'll see you in the next one.